Hello, and welcome to Golden Droplets episode number 38. My name is Ricardo Valls. I am the president and founder of Valls Consultant, and today we're going to start a mini-series on how I use SURFER to represent geochemical data. This will be a combination of Excel to process the data and SURFER to represent the graphics. So, once again, Golden Droplets, episode number 38. Enjoy! For this exercise, we're going to use the following database that can be downloaded from Mendeley using this link here. It's a group of data from an area from Nigeria, and it contains coordinates, some geology, the erosional level, the typical samples, and the quartiles for rare earth elements and gold mineralization. Also, the number of the sample, the real number on column J, and a simplified number on column E. If you want to learn about how to get the typical sample, the erosional levels, and the quartiles, there are other videos on my YouTube channel, which I will put a link here for you to explore. Another point is that in order to save time, it's very useful to organize your table having the first two columns as the easting and northing or latitude and longitude. So we will open SURFER. And the first thing that we're going to do, we need a base map. Okay, maybe you have an image, but if you don't have it, there is a simple way of doing this thing. So we start by creating a post of our data. And here is our data. And then we need to tell the system what coordinate system it has. So for that, we click on Map, Coordinate System, and we click on Change. And we know that our coordinate system is 32. I have it already on my list of favorite. So normally you will go here and you will find the one that you need, but I already have it down here. So, and the system is telling me that the map has a layer, which is a post SURFER that doesn't have the coordinate. We say, okay, we accept that, but then we go down here and click on Assign Now, and now all our data has the same coordinate system. Now, what we want to do is to export this square into Google Earth and then copy the image from Google Earth to use as a base map. For that, we need to limit the map to the borders, even without the coordinates. Like here, we can leave it, but I mean, it's not that important. We have this rectangle, and then you click File, Export as a KMC, like we call it base map. And we check that here in these two columns, you have the real coordinates, not the amount of pixels. So click Accept, and then you open Google Earth, go to File, open, double click on the base map, and you get here to the area. Adjust the tilt, make it a little smaller, and then with any clip tool that you may have, okay, you just click New, and we select that square there, and we will save it. as our base map. And now we have an image of the area. We also know the coordinates, the maximum and minimum coordinates for this section, which come from the Excel table. Now what we need to do, we will open a new map and we will import this image that we just took as a base map. Click here, base, you select the image. Okay. Now this image doesn't have coordinates, as you can see. It has only the amount of pixels as coordinates. So you click on the image and then on general, you click on georeferenced image. Now, SURFER will give you a good reference with just 3 points. I usually use 4 and I use the 4 coordinates from the border. So you click on this icon here, it selects point 1, 2, 3, and 4. So the only thing that you need to do is to come here and put the information. So for point 1, the minimum value for X for UTM, X east will be 358296, and also the minimum value for the UTM north, which will be 680167. Then point 2 will have the same elevation, 680167, and X will be the maximum value of X, which is 428079. Point number 3 will have the same UTM east. So we'll repeat this number here. 428079, but it will have the maximum value for the UTM north, which is 739113, and the last point will have the same coordinates as the beginning, so 358296, and the same UTM north, 739113. Now notice in this column the error that we had. Now when I press enter, this column will value probably going to be near to 0 because these are very good coordinates. So exactly, so we have our image georeferenced. When we have that, we just click on the first icon, update the map. We say yes, we say accept, we can close this thing, and now we have a base map that has the coordinates of our system. To this, we can add now the post, the values, our post, and we can do this 2 ways. We can just click and drag this thing here, but I'm going to do it in the best way, which is sooner. I just click the map, and here on layers, add layers, I will add the post, and it will be already in the map. So this is how we do the base map, and we have our factual map. Of course, there are other things like cosmetic that we need to do, like select a scale that will be proper for our map. We select a 4000 scale. We can put the names like UTM East, UTM North, also, it will be useful to have a scale on this map. So for the scale, we just click on Map Tools, Add Scale. It's very simple. I prefer the double bar alternate. And I also select the subdivision and I make it thinner. I also select the blue color for the scale. I like it better. So that is our scale. And what else? We will need to have a north arrow here. Now, if you put the north arrow, just like insert a symbol, like we put it here, and then we go to point, and we select here north arrows, and then we select here this one, and we'll make it, I don't know, 2 centimeters, 3 centimeters thick. Okay, and I add, select and adjust it. Okay, that's it. I can change the color to white, so it will be easier to see. Now, what happened is that if I need to change the position of the map, you see, I lost the position of the north arrow. So the way of doing this is very simple. Let's delete this. We click again on the map, and we click on Add Layer, and we click to add an empty base. Now, we click on that empty base, you see the red arrows, meaning that this layer is selected, and then we repeat the same thing. We put the sign, okay, and the sign is here inside. So we go to north arrow, we select this one, we make it 3 centimeters, and we make it all white. And then we click somewhere else. Oh, we need to adjust the position. So it would be okay. So we click anywhere else. Now, if I move the map, the north arrow moves with it. Next, we will do a map of the relief. And if you don't have information about the faults, I will show you an interesting way that you can get some information about that. So we will start with a new map. We will go to grid, and we will click on Variogram. Now, Variograms is one of the most important part of the processing of graphical data. Because of that, I will dedicate a full episode to that probably the next time. And also want to say that SURFER has an excellent way of processing variograms. Variograms will give you the national orientation or asymmetry or anisotropy of your data. For now, we're just going to make the variogram. Just look at the way we do it. We select the map as easting, northing elevation. That is okay. We click accept, and we get our variogram. There are several things that I do for cosmetics, like I like to leave just the name of elevation. I eliminate the subtitle. And one thing that is very important, I will click on the variance. And our objective is to find a curve represented by this blue line that will intersect this dotted line as close as possible to the left. Again, I will not go into an explanation. I will try rapidly to find the best model. And usually if you just go to model and click on AutoFit and click OK, it will try to do it, but in this case it didn't work. So I know there are three basic types of variograms. So I'm going to try. First, I'm going to remove everything. I'm going to add an exponential one and click on AutoFit and OK. And I get a line that is more or less what I'm looking, intersects the graphic here at the left, but it's not the best way to go. So I will try to remove that. I will try the logarithmic and click out of it. And this one shows a much better result, okay? And for the time being, I will just use this variogram. Now that I have the variogram, I go into grid data. I select my table. It's okay, east north elevation. I will select kriging as my main method. I will click next. I will get the variogram from the image behind, so it will get adjusted. Then I can skip to the end, and I will name this file elevation kriging. Then I will just click on finish. Now, if I open a new page and I will create a new map, like a contour map, using my elevation kriging, this is the map that I obtained. Now, as I said, I wanted to determine the possible location of faults, etc. So for that, we go to Grid and click on Calculus. In Calculus, we will go to the ring model and select aspect. We will select our gridding file, elevation kriging, and we will call this aspect. And we will click OK. And let me eliminate the previous map, just leave the map of the aspects, and I'm gonna change the color, the type of color, so it will be clearer. Instead of using a grayscale, I'm gonna use the rainbow. Okay, and what I'm looking here are, we want to get the red spots. These are the ones that are indicating the strongest changes in the aspects of the slopes, which will probably mean the faults. So say okay, and then I will go here in levels to advance, edit levels, and I'm going to eliminate all those. We leave the 62, we leave to 80 only. And then we click apply. And here you can see where are the possible faults. So to do that, go to Map Tools, and we will click on Digitize. And we will digitize the possible location of our faults. So I will assume that there is one fault here. So I'm going to click 1, 2, that's my first fault. Then I will leave a space, blank space here. Then my next fault will be this one, 2. Probably there is one from here to here, from here to here. And it's probably one going this way. I'm not going to make this too complicated. That's it. So we have 1, 2, 3, 4, and 5 faults. So for that, I will put the cursor at the 1. I will press enter, go back and put the number 5, which means that there are 5 faults. And then I will click File, Save As, and I will save it as a BLN file, which are calling faults. Now that we have our faults, we can go back to our variogram. Okay. And we need to do a new gridding, but this time we cannot use gridding, we will use inverse distance, because inverse distance will allow us to take into consideration the faults. So again, grid data, we select inverse distance, we select our data, easting, northing elevation, click next, and here in the anisotropy, we will use the anisotropy is 2, and the angle is 17.73. And then here in faults, we will just open our fault file. And then we can click skip to end, and we will save this gridding file as elevation ID with faults, and save. And if we open a new map with this, home, contour, you see the faults here. For the rest of the study, we will be using these faults, and if we want to add these faults to our base map, it's very simple. We just can click on this, copy, go back to base map, press paste, and just add the contours at the base. We need to make the right here, and you see the faults here. Again, the elevation, we can click on the levels. Okay. 1. Usually in geology, we use the rainbow, which is the normal coloration that we are used to use. And you can, of course, change the elevation interval. For example, you may want to do the contour intervals not every 10, not every 5, but every 10, or you can make it not every 10, not every 5, but every 2. That's it. That is how we do the elevation model using ID gridding, so we can take into consideration the faults. Another map that is useful to do with the elevation is the 3D model, so 3D surfaces, or also color relief. But if we go 3D surface with faults, this is the map that we obtain, and we can, of course, rotate it like this. And also we can have a 3D view of the model, which can also be rotated, and you can see here the fault. This is a very useful view if you want to prepare a presentation. So that's it. That is how we deal with the elevations. And on our next presentation, we will be talking a lot about variograms. So until next time, have a great day. And variograms is a very interesting mix between art and science. Of course, there is a way of getting to a variogram by try and error, but I will show you how I usually do it. It's a shorter way. First, you must understand that there are basically 8 forms, 8 types, 8 models of variograms. And SURFER offers all these and many more. So when you get an histogram, what you need to do is to figure out to which model your curve is more likely to be related to. So if your curve is like a little curve starting at the 0 point, well, that will be an exponential model. If it has a curve here and then another one here, that will be probably a Gaussian model. You must also know that all these models, you can add the nugget effect, so it will not start at the 0 point. Other models are the quadratic model, the rational quadratic model, the power models. This is one that is very interesting and very frequently found in geologists. It's the only one that I know that has this negative type of curve, like all the other ones are from left to right going up with a curve like this. This power model, when the value of H, and we will talk about that, is between 1 and 2, it will make a curve like this. And then you have the more simple linear model. And remember that, as in everything in geology, keep it simple, stupid. Try to get the simplest line that explains most of your data. And do not try to combine many models that you may get an overfit. I mean, 1, 2, 3. You may get an overfit of the curve, and that's never good enough. The wave or whole model have used this in soil sampling when you don't have a very regular grid. It creates very interesting maps like the circles, independent circles. So just use it with care. And that's it. You also have 1, 2, 3. And lastly, you have the bent-spherical model and the cubic model. Of all these, as I mentioned, the cubic model, the power, the linear model, of course, the power one, and the exponential models are the most commonly found in chemistry. This article, this little PDF, you can find it online. I will put the link in the description of this video, so you will have it hand. So let's go now into SURFER and try to do 2 or 3 different varograms and see how this principle works. See you there. The data that I will be using for this webinar, you can download it. You can find it online just by typing the DOI number. It's on Mendeley data. It's an excellent site to collect and keep your information online, so you can share it like we will be doing now. Just to remind you how we start to do a variogram, you go to grids, new variograms, and then you select the file that has your data, and then you select which element you want to do your variogram. You click accept, and you get the variogram to work with. So let's start with this one here. This is a variogram from arsenicum. And I always do a little bit of cleaning or just changing the format. I go to plot. I take out the subtitle. I just leave the name of the element. And I always select the variance to show. This is very important because the line of the variance, what we are trying to get is an intersection between our blue line and the line of the variance. Sometimes, like in this case, the variance is so high that it's not in the graphic. This means that no matter how much we tweak with this element, we are not going to get a very good variogram at all. So let's see what we can do. First, we go to model, and we will let SURFER to try to do an auto fit of this graphic. So we just click on auto fit and we select OK. And you can see that it changed a little bit. This is the nugget effect, which is now around 45, 44. And this is the line. Okay, we could try, remember that we are looking for figures. We could try a logarithmic one to see how it works. So I will remove both lines and I will add the logarithmic, and then I click on auto fit. Okay, and I get a much better line than just a line. I could make it to go a little bit higher. Let me try to put this on 12 and see what happens. Yes, that is much better. So you see, you get an idea of the general curve that will better fit the model, and then you start tweaking and adding little bits. One thing that I always add to this graphic, using the cutting tool that comes with Windows, I take a cut of this, copy, and I paste it on the graphic. So I will have information about what type of model I use and what are the conditions. As you can see, we have an anisotropy of 142 degrees for this data. So this is good. We save it as Variogram arsenic. Okay, let's go to the next one. The next one is for cobalt. Again, I do the little formatting. Take this off. I take the subtitle on. I put the Variogram on. And you see here, the line of Variogram is very close to this, our blue line. What we want to do is for this blue line to intersect the dotted line as close as possible to the left side of the graphic. Again, we will let Variogram, we let SURFER do the auto fit. And it doesn't work very well. You see the line doesn't intersect the thing. So we can try, and I will go here to the slope of the line. You see it's a very, very small slope. I'm going to change that. Again, this is trial and error. Oh, that's too big. So I need to add a couple of zeros. No, still too big. Let me put this at 7. Okay, now it's cutting, but it's too, the nugget effect is too high. So I'm going to go back to nugget effect and put a lower. And there I have a line that is very good. I could increase the slope of the linear, or increase a little bit the nugget effect. Yeah, that is perfect. So again, I just select the linear, go to my cutting tools, new tools, and I cut this, copy, and go here and paste. And now I have my data for the cobalt, and I can see the anisotropy here is 0, means it's north, true north. One last example, we go here, we have the iron. Again, I do the cleaning. Okay. So our objective is to get a line, a blue line that will cut the dotted line as close as possible here. Again, I always try, give SURFER a try to see if it can do it. And it did it, but It's not taking into consideration any of these points down here. So this could work, but I will try with, I'm going to remove both, and I will try with an exponential line first. Okay, out of it. Okay, and I get a much, much better cut. I mean, this is perfect. I don't need to do anything else with that. So again, with my cutting tool, I go and cut this thing, copy and paste it. So for iron, I can see I have a 43, almost a 44 degrees of anisotropy. And this is how we do, the variograms. Once you have the variogram, let's save it. So this will be variogram for iron. You can go and start doing the gridding, the actual gridding, by you say grid data, you select the file, you select the element, which is in this case iron. And on the next step, you select to get variogram. You see, you got the variogram, and then you can skip to the end. We will save this as iron. And we will create a map, a contour map. We click OK. I just take off this and this. And this is the map of the iron. As you can see, it has the 42 degrees of anisotropy that we had. We can, of course, when we did this, we could also add the faults that we discussed in the previous episode, and we will get a much better chemical representation. So this is variograms. I strongly recommend that you train yourselves. You will get the eye for the different curves, and it will be a much faster process, but this is basic. This is very important to do. On our next episode of this series of SURFER, we will be talking about erosional level. Until then, have a great day. Today, we will discuss a very interesting aspect of geochemistry. As everybody knows, usually we cannot pinpoint the depth of the signal that we are discovering on surface. But there is a method that is very common in Russia. When I was a student there, it was given to me like, normal information, like 2 + 2 is 4. And it was called determining the erosional level. Basically, using geochemistry, we can determine the position of the erosional level with respect to the ore body. And therefore, using this method, we can have an idea of how deep our mineralization source is, or also is a very good method to categorize our anomalies and define where are we going to study first. Here, this table that, as you can see, you can find in following this link here, this DOI. We have an example of a raw data, normal data converted all to part per billions. Okay, so this is our normal data. The method that we are talking about is called the erosional level. And I call this the original. This is the one I learned when I was a student. And it basically, the theory says that when you have the formation of a deposit, there is always a group of elements that will tend to form on top of the deposit because they are more mobile, and those are called supra elements. And there will be a group of elements that tend to form below the ore body, and those are called infra elements. Examples of supra elements are mercury, barium, silver, and others. Examples of infra elements are cobalt, nickel, chrome, etc. So basically,
If you make a coefficient dividing the supra elements by the infra elements, and you get that coefficient gets a value that is very, very big, that means that the erosional level has not yet reached the ore body. That is a very good thing. But if you get an erosional level, a coefficient that is very small or negative, that means that the erosional level has already reached this part. So even though that you may have an anomaly, this is a residual anomaly because the ore body has been already eroded. Okay, so there is plenty of reference about this method. Here you can see some of them. Because many people ask me, well, where can I find more about this thing? You studied at the university, but want to read it. So these are some of the books that talk about this method in details. And it also offers a list of from the most supra to the most infra elements that you can use. So how do you calculate the erosional level? It's very simple. Let's say we will use here 3 elements, like supra elements like barium, iode, zinc, and 3 elements infra elements like cobalt, nickel, and chrome. The first step is to standardize all these values so the difference in their concentration doesn't affect us. The formula for standardizing, you can see it here, is standardized by the mean and the standard deviation for each element. Once we have standardized all the data, then the formula is very simple. We take the integral part of the sum of all the supra divided by the sum of all the infras, and we get these columns here. For example, that -1 means that we are down here. That 4 means that we are up here. Okay, a value of zeros, ones, etc. Maybe we are already at the level of the ore body. In any case, the negative values are the ones to be avoided. Now, this is the way I was taught this method. But later on, I realized that there is a factor, a physical factor that is not included in this formula. This is basically a pure geochemical formula. And the factor that is not included here is the elevation. And as everybody knows, erosion has more force on high elevation than on lower elevation. So I added to the formula a coefficient, which was the elevation, okay? And again, it's the same method. We standardize everything, and then the formula will be the same, but multiply by this coefficient here, the elevation coefficient. And as I did some graphics and I saw, okay, I'm getting a much better idea of the erosional level because I'm taking into consideration the elevation. Well, the next step was to do a little comparison of all of these methods. Like this is a normal method, this is a normal method, but multiplied by the elevation. And then I just standardize those two columns. As you can see here, that is the erosional level, the normal one, pure geochemically. This is the erosional level standardized. Okay, the same thing, but standardized. Then this is the erosional level, taking into consideration the elevation, and the same thing, standardized. And finally, I added both values and direct added and the absolute value of that sum. And as you can see, this last column, the absolute value of the sum of both erosional levels, give us the best result for mapping the erosional level. So this is how we get this column. And I'm going to show you now our data, the data that we have been using. This is, again, you can check this database here at this DOI. You can download it from there. And I have already here the column of erosion or erosional level. And we're going to use now SURFER to process this erosional column. So we go to SURFER. That was our last map. We start by defining the variogram for the erosional level. So grid, variograms, new variograms. We select our data. We select here erosional level. And we get this variogram, which is basically, well, the straight line will probably do. Okay, let's do our usual cleaning. Yeah, that line is very good, but let's try to do the autofit and see if it gives us, oh, yes, it gives us a much better line. That will be the variogram for the erosional level. So as usual, I will take my cut tool, cut this section, copy, and paste. And I will save it as variogram elevation. I have it done previously, so I will not do it again. And then again, we go to grid data. Because we have faults, and the faults should affect the erosional level too, we will use invert distance to a power, and select the erosional level. The anisotropy, the ratio is 1:242. The anisotropy, the angle is 90. Faults, use the fault, and then we can skip to the end, and it will be called erosional level. And to save some time, I'm gonna click on create a new map, and it will be a contour map. So I click finalize, accept. I will take off the variogram. So this is our map for the erosional level. So as I mentioned, we need to figure out which are the values that are low. So again, we click on the map, we go to levels, click on advanced, edit levels. You can see all the negative here. So I would start by deleting everything that is bigger than 1. Okay. And then I will delete everything that is between 10 and -1, because I really need to know the lower level of the erosion. So I will put this as a blank. I will put this as a grid with no opacity. I use usually the color brown for this. Okay. I don't need levels for that. I don't need a line for this. And press apply. And I can, okay. And then I need to put the fill contours. And these are the areas that had been eroded in our map. So if I get an anomaly somewhere here, I will test the latest one. This is a way of categorizing the anomalies into more important or more prospective and less prospective. As we did the last time, we can just take this copy and go back to our map and paste it. Just drag this down here. Okay. You can see all the erosional levels here, and that will be the base map. that we will be using for our representation of the anomalies, which will be the subject of our next webinar. So here you are, erosional levels. I hope you find this video very useful. Until next time, enjoy. And here we are on the last section of this mini series about how to use SURFER to represent geochemical data. And not only to represent, but also to interpret some of these geochemical signatures that we are getting. For this last part, which will be how to present your data in a way that anybody will understand. And I'm going to be introducing you to a method that I have developed called the Quartile methods. And we will be using our common table, Excel table. Again, as always, you can download this data set from this site. And we're going to go directly to the section of quartiles because I already have several videos explaining how to get the different parameters. And the objective of all the processing is to get as many equations, as many formulas that will represent the potential mineralization in our target. In this case, for this data set, we have two types of mineralization. We have a gold mineralization and a rare earth element mineralization. And we are going to explain only one, the gold, just for time constraint. So let's jump directly to quartiles. Here, I just put the different parameters that we use, that we obtain during the processing of this data for gold. So we have 1, 2, 3, 4, 5, 6, 7 parameters, and of course, the value of gold. But as you can see, the coefficient, each coefficient varies extremely by the magnitude. Sometimes it's millions, sometimes it's 0.1. So if you want to represent all this in a map, it will be extremely complex to read. You're going to need to have different scales, etc. So the quartile method, and what is a quartile? Quartile is when you have your population of data ordered from the smaller one to the big one. You divide the population in quartile, in 25%, and each one of them is a quartile. So 0 to 25 is the first quartile, 25 to 50, second quartile, 50 to 75 is the third quartile, and above 75 is the fourth quartile. So that way we can convert all these numbers into quartiles, okay? But then the next step on this processing is, I said that if this data, for example, is above the third quartile, I will put a number 5. If it is above the second quartile, I will put a number of 4. And if it is below, I will put a number of 3. So this is the formula here. Okay, so as you can see, I converted all these different range of numbers into a column that only have values of 3, 4, or 5. And again, the formula, as you can see up here, is if the original value is bigger than the third quartile, then I will put a number 5. If it is bigger than the second quartile, we'll put a number 4, and then if not, it's a number 3. And the quartiles, let me go down here for a second. This is where you determine the quartiles. And the formula of the quartile is very simple. So quartiles is, you write quartile of all the data, comma, and the quartile that you're interested in this case is 3, and the lower one is 2. So now we have all our data converted into values of 3, 2, 5. The next series of columns is, this is exactly the same as this group here. The only thing is that I eliminated the formulas. I just copy and paste this as numbers, eliminated the formula, because sometimes Excel's, when working with tables that have formulas embedded from previous formula, it sometimes make mistakes. So it's easier just to grab all your data, okay? You just copy it and you just paste it as values. That way, you see, we have eliminated the formula. These are just numbers. Now, what does this mean? For example, this first sample where every single value is 3. That means that this sample, for all the components that we are exploring, always has very low probabilities of having mineralization because the value is 3. Now, if I had a sample that all these parameters will be 5, that will mean that this sample is very, very probable a gold target because we have it score above the 3rd quartile for all the possible combination of formulas that we are exploring. So what could be the maximum value for a sample that have 5 on all these things? It would be 40 because we have 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. So the way I create my quartile map is as follows. I say the sum of all these values multiplied by 100 and divided by 40. 40 because I have 8 columns and the maximum value for column is 5. So 5 by 8 is 40. So this column here, the gold quartile, is telling me directly in percentage, what is the percentage or the probability that this sample will be mineralized. So we have been, with this method, we're able to convert, I don't know, 50 maps, 50 columns of data into just one single layer, expressed in probabilities from 0 to 100, because it's giving you the probability of each point to contain or not mineralization. So once again, very simple. You convert all your data to quartiles and you use a formula that said that if the quartile is bigger than the 3rd quartile, you will put the value of 5. If it's more than the 2nd quartile, you will put the value of 4. And if it is less, you will put the value of 3. These values are subjective. You can put whatever value you want, because anyway, at the end, what we're going to do is we're going to add all those values and divide it by the amount, the maximum amount of value that we can get if everything here was 5, which would be 40. So if we had a case of 5, 5, 5, 5, 5, 5, 5, we'll have 40 by 100 divided by 40 equal 100. This is the column that we're going to use in our map. So you can see we're going to be representing a map of the probabilities of each of these samples to be in a mineralized zone. So we create our SURFER table, which the last one would be looking something like this: the east, northern elevation, the geology, erosional level, a typical samples, the quartile for rare element, and the quartile for golds. And now we're going to go to SURFER, and we're going to represent our quartile of gold. So here we are back to our SURFER map as we left it last time. Just to make it this clearer, I'm going to deselect the elevation. So the first step will be to create the variogram of our gold quartiles. So we will do our variogram, our data set, and we select the gold quartile data. We have our line here. Probably a straight line will work well. I just do my usually formatting. Make this, put the, whatever. Yeah, this is probably going to be a good line, but as always, let's see if
SURFER can do a better line. No, this is not one of those cases, so I will leave it like that. I can manually change a little bit here, like I could make the slope a little bit bigger, too big, 25, 23. Yeah, that will be much better. So using my cutting application from Windows, I will cut this thing, copy, paste it here. And I have my anisotropy 1 and angle 0. Now that I have my gold quartile, I'm going to do the gridding of the data, and I will use the inverse distance because, as you remember, we have faults. So grid data, inverse distance, we use our table, we use the gold quartile, click next. The anisotropy, as I say, is 1, 0, that doesn't change. The fault, we open our fault file, and we can go to the end, and we call this gold quartiles. I'm going to put another directory here, gold quartile. Okay, and I will have a new map, a contour map. So I say close, say yes, I will eliminate this. So this is our map of gold quartiles. And again, this map is a representation in percentage of what is the potential of each sample to be part or not of the gold mineralization. So what we should do, very easy, is to go to here to levels. We change this to advanced. We click on edit levels, and we're going to leave only, we have up to 90. So let's say we're going to leave 75, 80, and 85%. So for that, we can delete, but we can just write 75, 80, and 85. And then we delete the rest. We select all the lines as straight lines. And for the colors, we want the labels. Yes, let's put the labels. For the colors, I use standard patterns that are recommended by the art industry to be used with data that are contiguous. So I will put these 3 files in my Mendeley. So if people want to download them, they can download them. Go for my lower level, file, and I will put my level 1, my second level, file, my level 2, and for my third level, file, my level 3, and I will press OK, and I will press OK again. And then, of course, I need to fill the contours and provide a scale. So here is our map. This is the map that anybody will understand, because we're just saying the possibility in percentage of these areas here to contain a gold deposit. Okay, you can even be more restrictive. You can say that you want just to eliminate the 75. Okay, and this is the map that you will present to your bosses. And again, we can just copy this map, go back to our base map, paste, dragging up here, and this is the map. Now, as you can see, this area here are at least partially covered by an erosional zone. So this one here is completely covered because the anomaly has been already eroded. It may be that this just outcropping. So take a look. This one here is between two little erosional targets, but this one here is very good. This one here is close to an erosional, but it's not touched by an erosional. So there are several points. And remember, these are 80% probability that you have a gold deposit. So this is the way of representing multiple maps in just one map, the quartile map or the quantic map for geochemistry. I hope that it will be very useful for you. And with this, we finish our series in SURFER. In this series, we started by, making a base map, determine the linear meta-analysis, partial linear meta-analysis, the erosional level, and we finalize it with representing the geochemical data in your map. Again, the quartile method is the perfect way of representing multiple anomalies in just one map that represent the probability that this point here has 85% probability to be a gold deposit. Once again, thank you very much for attending, and I will see you in the next Golden Droplets episode. Have a great day.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.